Welcome everyone to our introductory video on the quantum model of the atom. You may have been introduced to aspects of the quantum model in previous chemistry courses or in a biology course. We're going to start from scratch here and assume that you don't know anything about this model of the atom. Our goal for this lesson is simply to describe the key features of the model. We'll be going through it in detail, and then we'll be exploring these different features and how we understand the atom in more detail throughout this unit. Going into this lesson, you should have an understanding of the key features of the Bohr model of the atom, and that will help you understand where we're going with the quantum model. Before getting into the structure of the atom as described by the quantum model, we want to start off by just talking about what it means for an atom to be described in the quantum nature using quantum theory. In the late 1800s and early 1900s, there was mounting experimental evidence that the energy that's associated with matter, so atoms and molecules, was discrete rather than continuous. So what do we mean by discrete? One way to think about it is that it comes in little packets rather than something that is radiating at us like we experience it. So, for example, if you open an oven door when the oven's on, you feel the heat coming at you. It doesn't feel like raindrops hitting you one at a time. You just feel the constant flow of the heat. That would be continuous energy. When we talk about energy being discrete, that's thinking about like raindrops, energy coming in discrete little packages that is bombarding us with that energy. So when we use the term quantum, it's always describing some sort of discrete aspect of describing atoms, electrons, energy, something along those lines. Another way to think about the quantum nature is comparing a climbing up a hill on a continuous path versus climbing up stairs. As we're climbing up the hill on a continuous path, we can actually be at any sort of vertical elevation. Whereas when you're climbing up steps, you're on one step, and then when you take a step up, you're on the next. You can't float in between the two steps. So the difference between like a ramp and climbing stairs. So a ramp or a continuous path would be continuous, whereas climbing up steps would be discrete. You're on one or you're on the next. So it might be helpful to keep these analogies in mind as we start describing the atom. The second piece of theoretical framework that we need to introduce before talking about the quantum model is this idea that there are some limitations in the types of measurements that we can make when we get down to a very small scale. These limits are not based upon our instruments, so how precise the instruments are. It's built into nature itself that there are certain pairs of measurements that we have limits on the level of precision that we can reach. Describing the location of electrons is one of these limitations in measurements. And as a consequence of that, we can no longer speak of an electron being in a precise location. So think back to the Bohr model where we drew those circular orbits and said, okay, we had an electron at this distance from the nucleus. It's no longer appropriate to talk about a fixed distance or a particular distance from the nucleus. It's more appropriate to talk about the electron locations in terms of probability. So the term that we'll be using is regions of high probability of finding an electron, or the location of most likely to find an electron there. So some of the language changes, and the reason for that is due to some theoretical advances in the early 20th century that put some limits on how precise we could be with certain measurements. The final piece of theoretical foundation that we need to talk about is the idea of particle-wave duality. This is an idea that was seen in terms of energy with Einstein's photoelectric effect explanation, as well as the theoretical work done by a French physicist named de Broglie that showed that when we get down to the subatomic level, particles can exhibit both the properties of waves and of particles. When you think of waves, think about how we think about how sound and light travel as continuous waves that change in frequency or can change in amplitude as they travel. So what was shown is that when we get down to the subatomic level, specifically in our case talking about electrons, that these particles can exhibit wave-like behavior. And this is very counterintuitive because we don't experience this at the everyday or like the macro level. So we can't really use analogies of thinking about electrons like little spheres to appreciate how electrons actually exist. So this is always one of the challenges with the quantum model, that we need to suspend our disbelief that electrons can do things that objects at the everyday level cannot. Let's get into the structure of the atom. Now, in chemistry, when we're talking about the quantum model, we're really focused on the electronic structure of the atom, as in where all the electrons are, where they're found, the shapes of the regions they're found, and so on. Why? Because as you know from previous courses, it is the electrons within the atom which govern the behavior of bonding, chemical reactions, physical chemical properties, and so on. So understanding the electronic structure will help us understand chemistry. So the central concept that we're going to introduce today is the idea of an orbital. I'm going to define the orbital in a few different ways. The first way we'll talk about it is just probably the most visual way of thinking about it, is that an orbital is the region in space that has a high probability of finding an electron. However, what we should also appreciate is that quantum chemistry or quantum physics is a mathematical science, it's a quantitative science. And technically, an orbital is the solution to a specific equation that's called the Schrodinger wave equation. We'll be leaving the math alone, but it's important to understand that there's a mathematical aspect that's central to what we're talking about. The orbital is a solution to a mathematical equations. In order to solve this equation and get this orbital, to get this region in space, we need to know four things. There's four variables that we need to know. So an orbital is the region of high probability of finding an electron. Another term which is introduced here is an electron's quantum state. So I said that there were four variables needed to solve this mathematical equation and describe the orbital. In chemistry, we often think of this as four properties of an electron that we need to know in order to describe its location. If you were to get into the math involved in here, you would see that these values are all integer values. And what the result is that it restricts the allowable energy associated with an electron. So just like the analogy we looked at previously, could give an electron this amount of energy or this amount of energy, but nothing in between. This should seem familiar from the Bohr model of the atom, where he had these energy levels, and an electron could be at one energy level or another energy level, but not in between. The first variable that we're going to talk about is called the principal quantum number. It's given the symbol lowercase n. The principal quantum number describes the average distance that an electron has from the nucleus. Or the way we usually talk about it is it describes the electron's energy level. The values for n that n can take on are just simply positive integers starting at 1. So the lowest energy level is 1. The next lowest is 2, 3, and so on and so forth. You're familiar with this because the principal quantum number is just Bohr's energy level. So when Bohr developed his model of the atom, he came up with the principal quantum number. The most important thing to understand is that these quantum numbers are associated with energy. And so as we increase the value of n, the energy associated with an electron increases. So that's why we call them energy levels. So as we increase n, the energy increases and the distance increases as well from the nucleus. The next variable or quantum number that we're going to introduce is called the secondary quantum number. And it's given a symbol of a lowercase l. I'll use a italicized L in this slideshow so that it's distinguished from the number 1. Spatially, this number describes the angular momentum of an orbital. What's meant by angular momentum? Really, it's talking about the shape of an orbital. Is it a perfect sphere, or is it kind of a lobe shape, or something different? In chemistry, we talk about these shapes of different orbitals, or these different possible values for angular momentum, as the different sublevels. For the known elements, there are 4 different sublevel types. So 4 different possible values. However, the quantum model predicts that more are possible. It's just that we don't need them for the elements that are known right now. The secondary quantum number depends on the principal quantum number. So L can take on integer values from 0 to n minus 1. For example, at the first energy level, when the principal quantum number is 1, there's only one option for L. It can only be 0. Now, 0 does not mean nothing. 0 here indicates that there's one sublevel, and L equals 0 sublevel type. When L is equal to 2, the integer values from 0 to n minus 1 are 0 and 1. That indicates that there's 2 sublevel types present at the second energy level. A 0 type sublevel and a 1 type sublevel. Even though we will talk a bit about the quantum numbers, since we're not doing the actual math with them, chemists most often talk about these sublevels in terms of their letter designations. The 4 letters that we use are S, P, D, F, and they each correspond to one of the values for L. When L is equal to 0, that refers to an S-type sublevel. And as we'll see, all S-type sublevels are spherical in shape. When L is equal to 1, we describe a P-type sublevel. P sublevels are bilobed in shape. And so on and so forth with D and F, which get into some more complex shapes. This is where we're going to end off for the first part of this video. In the second part of the video, we will continue on describing the next 2 quantum numbers, and then put it all together in a coherent picture of the electronic structure of the atom.